Welcome to the lecture series on reinforcement learning. In this video, we ask the question, why is novelty useful? Let us start with a short review of standard TD learning. At the top, we have the Bellman equation. And this equation connects the Q values for some state action pairs with the Q values Q of S prime at a later state action pair. And an important component is this transition matrix. Given I choose action A in state S, what is the likelihood that I arrive in the state S prime? Now, the Bellman equation imposes a consistency condition with the Q values QSA and the Q values Q of S prime A prime. And we have seen different algorithms such as SARSA, expected SARSA, Q learning, that all have the property that if the algorithm has converged, it has converged to a solution of the Bellman equation. We have added one extra component to these algorithms, and let's look here at this discrete state action graph in 2 dimensions. The goal state is here. We start in the lower right hand corner and take an action upwards. We take the next action, and then in the first episode by chance we arrive at the goal. Now eligibility traces say when I have chosen in my first state action going upwards, I have updated an eligibility trace, and then this eligibility trace decays over the next time steps to a lower value. But when I reach the goal, I update all Q values, and that means I also update the Q value of my initial state proportional to the eligibility trace and to the TD error, which is also called reward prediction error, RPE, reward prediction error. TD learning comes in 2 major classes. There's model-based TD learning and there's model-free TD learning. Model-based means that while playing, we learn a model of the environment. That means we estimate the transition matrix that under action A, starting in state S, I go to state S prime. In that sense, after we have played several actions in each state, we start to know the rules of the game. And if we know this transition matrix, then we can plan ahead. We can say, let's imagine that I take action A in state S, and what would be the next set of possibilities? 1 step ahead, 2 steps ahead. And that also means that we can update the Bellman equation in the background. This consistency condition of the Bellman equation that connects Q values Q of SA with later Q values Q of S prime can be updated in the background. And we can simulate action sequences without taking actions. Now, model-free does not learn this transition matrix. It does not learn a model of the environment. In that sense, it does not know the rules of the game. It cannot plan ahead, and it cannot update the Bellman equation in the background. It cannot simulate action sequences. Now, model-free, the strongest version of model-free, exploits these eligibility traces to keep the memory of the past state action pairs. And it also has V values and Q values, so it also solves the TD learning type Bellman equation, but it does it in a completely online causal forward in time fashion. Whereas model-based is not online forward in time, and in that sense it's also not causal. Now, standard reward-based TD learning starts with the rewards, and from these rewards we estimate Q values for rewards, the little index R, via the Bellman equation. And then, as I just reviewed, we can do this in a model-based version where we can update the Q values in the background without playing additional actions, for example, using prior prioritized sweeping. And then there is the other type, model-free, where we cannot update in the background, but we typically use eligibility traces. And so we can now say, okay, suppose we use the model-based version, then I would calculate model-based reward-oriented Q values, or I use a model-free version, then I have a different set of Q values based on the model-free approach. Now we want to discuss novelty. So let's replace rewards by novelty, the momentary novelty values. Then we can construct in the same way a consistency condition between Q values SA and Q values S prime A prime, but these are now Q values based on novelty. And then we can estimate the Bellman equation either in a model-based version using prioritized sweeping, which gives Q values that are model-based with novelty instead of reward, or we can use it model-free with eligibility traces, which then is Q values model-free but novelty-based. Now, let's see how this could work. We consider here an environment with 10 states. There is a unique additional goal state. That's the only state where we have a positive reward. Now, the states are discrete and we always have 4 actions. For example, if you take action A2 in state 1, you go back to the same state. If you take action A3, you go to the next state. You go to state number 2. With action A1 or A4, you go to one of these states 8, 9, 10, which we call trap states. Intuitively, it's like in a child's game, back to start. And then out of these trap states, there's always one action that leads back to state 1. Now, this assignment of actions to states is deterministic, fixed, but randomly assigned at the beginning. So I said action A3 in state 1 leads forward. Now action A3 in state 3 leads back to the same state. And here, for example, it's action A1 which leads forward, which means here it's action A2 and A4 which lead down to the trap states, and so forth. So this forward action is not always the same button, the same action button, but it's always a different button for each state. Actions are deterministic, so it's fixed, but randomly assigned. And now I ask you the following question. Suppose we start in state 1. It's the very first episode. We have not seen the environment before. And so let's start with a random policy. Question: how many actions on average will you play before finding the goal? Well, it will be a lot of action, say at least 100. Will it be between 100 and 500? Will it be between 1,000 and 5,000? Or will it be more than 10,000? 10 states, 4 actions each. Intuitively, what do you think is the answer? Well, it turns out it's more than 10,000 actions. So, without any strategy of how to go through the maze, and you don't know the structure of the maze, you just see states. You don't know where you are. Without any strategy, it takes a very long time to reach the goal for the first time by chance. So we need a way, a more systematic way to explore the environment. So let's focus on the first episode, and that means before any reward. As I said, the reward is only in the goal state, and you have not yet seen the goal state. So the reward is always 0. Whatever you do, 0, 0, 0, 0. And somehow we have to improve the exploration. Now, a first idea that may come to mind is optimistic initialization. What is optimistic initialization? We have talked about the Bellman equation, which connects Q values. It's a table of Q values. We are in a tabular setting, and we can initialize each value in the table with a fixed but very high value. If you say the reward at the goal is 1, you know this, then you say I initialize with 10. And so it will slowly move down. In fact, it will very slowly move down from 10 to low values, because if you choose a gamma of say 0.9, then it goes in small steps. Moreover, how would you generalize once you have found the goal for the first time? How would you use the same Q values for episode 2? Some Q values might be still as high as 5 or 4. So it's not the best of all ideas. So what else can we do? And this is where novelty comes into play. I will argue that novelty encourages exploration. So let's call novelty at time t by the little red n sub t. Now we will have separate Q values, Qn for novelty, separate from the Q values Qr for reward. And while in reward-based Q learning we had a TD error, a reward prediction error, we now have similarly updates for the Qn values, for the novelty-based Q values that are not driven by the little r, but by the little nt for novelty. The rest is the same. And this term in the square brackets, this is called the novelty prediction error. And suppose we have played some strategy. It does not matter which strategy for the arguments in this environment. And now here we plot the number of visits, and then the novelty is this transformation of the visit count. And you see that if you look at state 8, 9, and 10, 8, 9, and 10 are the trap states. You go quite often to the trap states. And therefore, the number of counts of the trap states increases rapidly. But the number of encounters, for example, with state 4, increases much later. And this means that the novelty of state 4 goes down much later. The point T star is marked as the point where we encounter the state 7 for the first time. So this is encounter number 1 of state 7. And you see at this time the novelty of state 7 goes down. And if we take a snapshot of the all novelty values for the different states in this graph, we see that it has a nice shading from dark blue, very low novelty, to bright green, very high novelty. And this suggests that novelty is a good indicator to guide you through this maze. And that's what we are going to explore in the next video. So we want to use novelty Q values for choosing our action policy.